Hi everyone, I'm Modarressi and I'm delighted to present you our work AdapLeR, an approach for speeding up inference by adaptive length reduction. This is a joint work with Hosein, Mohebbi and Mohammad Taher Pilehvar. There have been various efforts in reducing inference time in BERT-based models. Methods such as module replacement, quantization, knowledge distillation, and weight pruning. However, all these methods suffer from being a static model regardless of their input. Another branch of pruning techniques is called input adaptive pruning, where in these approaches, speed up could be gained by neglecting several layers, such as early exiting, or by dropping some tokens. AdapLeR and some other approaches are within this token level input adaptive pruning group, and we show that we outperform them in various tasks. Well, for a start, AdapLeR's goal is to reduce the number of token representations in a progressive manner. This means it could drop several tokens at each layer, that it reduces the number of tokens passed for the next layer, which in total this leads to a reduction in inference time. It is worth noting, though, that this should happen with the least amount of performance loss. During inference, the main challenge is figuring out how much each token is contributing to the final prediction. We've implemented an extra component for each layer that estimates the amount of contribution of each token based on its representation. After the CP computed the contribution values, a trainable threshold separates the retaining tokens from the dropping ones. But we keep the CLS token as the final prediction is based on its representation. To train an AdapLeR-based model, there are three challenges: training the CP of each layer, how to apply the removal during training, training the threshold levels. Starting with the CP, we used a model that is fine-tuned on the target task and extracted the contribution scores using a gradient-based method. Then, each layer's CP's loss is computed using KL loss. And finally, using a weighted sum based on the layer numbers, we added the CP's loss to the classification loss, cross-entropy loss, multiplied by the hyperparameter gamma. Now, about removing tokens during training. The same removal mechanism during inference is not used due to the discrete characteristics of dropping a token or retaining one. And since we wanted to apply gradient backpropagation to the model, we implemented a soft removal function to mimic the removal of the tokens in a gradual manner. This is done by incorporating the attention masks that as they are summed with the key query dot products before computing each layer's attention. In the soft removal function, as the contribution value drops lower than the threshold, it rapidly drops in the amount of attention it gets. Also, since we trained these thresholds, we opted to a continuous function, and therefore contributions above the threshold also get a negative attention mass value, but with a lower degree of slope, of course. As the training goes forward, the slope before the threshold increases, while the other one after the threshold decreases. Ultimately, this tends to reach to a point that it's similar to a discrete removal. For training delta L, we use the attention mask to define length loss, and the length loss is multiplied by phi as a trade-off tuning hyperparameter, which tunes the trade-off between speed up and performance. Note that this loss only tunes the thresholds, while the loss in the CP training that we mentioned earlier is used for tuning the whole model. Now, here we have BERT's results on several different classification tasks. We also added distilled BERT results as a common static efficient model. And before we continue on the table, we mentioned there are also other models which reduce the number of tokens during inference. TR-BERT uses RL for training, and therefore its large action space limits its reduction capability in only 2 or 3 layers. And PowerBird considers attention as a metric of token importance, which is questionable in terms of faithfulness to the final prediction. Here we add the results from these two models, and finally AdapLeR, which shows competitive results and outperforms the other two token-level pruning approaches in most of the tasks. For a better comparison, these plots show the accuracy speed-up trade-off curves for two tasks on the three models. This also confirms that AdapLeR presents more promising results. To have a better understanding of the CP's output, here we show the contribution scores outputted from the CPs. As we can see here, it seems that the CP's return scores do seem plausible. Therefore, we went another step further and checked the alignment of this return scores and three other explanation methods with rationales from a dataset that included human-labeled rationales. The false positive rate shows how much these explanations misidentify the tokens as important ones, and the mean average precision, MAP, shows the alignment of the top scores with the rationales. And as we can see here, the CP scores improve layer after layer, returning less non-important tokens. And that's all about AdapLeR. Thank you for your attention, and feel free to contact us in case you have any questions.